Hi, my name is Aina Nurul Kasif and I will be explaining what is related rates. In calculus, related rates is a concept that deals with finding the rates at which two or more related quantities change with respect to time. It is commonly used when the relationship between the variables is given as an equation and you want to understand how one variable's rate of change affect another. So why we use related rates? We use related rates in problem with dynamic system when quantities are changing over time and their rates of change are connected through a functional relationship. We also use it in indirect measurement because it's easier or only possible to measure the rate of change of one quantity, and we need to deduce the rate of change of another.
Hi, my name is Nurul Ain. Finally, we use it in real-life applications where many practical problems involve changes in physical quantities, such as the rate at which water flows into a tank, the rate of shadow lengthening, or the rate of expansion of a balloon. Move on to the problem statement. The question is, an open box is to be made from a 15 cm by 20 cm piece of cardboard by cutting out squares of equal size from the corners and bending up the sides. What size square should be cut to obtain a box with largest volume?
Moving on, problem solution. The first thing that we must do is list down all the equations and create a volume formula for the open box. Let y become the side length of the square that will be cut. Length of the open box will be L, which is equal to 20 minus 2y. Width of the open box will be W, which is equal to 15 minus 2y. Height of the open box will be H, which is equal to y. The volume of the box will be V, which is equal to L times W times H. When we times all the equations, we will get Vy equal 4y cubed minus 70y squared plus 300y. The next step is to derive the equation. After deriving the equation, we need to let the derivative equation equal to 0 and find the values of the variables, which is y. Our derivative equation is v prime y equal to 12y squared minus 140y plus 300. Our maximum value is v prime y equal to 0. When we simplify the equation, we will get 3y squared minus 35y plus 75 equal to 0.
The third step is to get the variable's value. We need to use the quadratic formula since the value of the variables is a whole number. After using the quadratic formula, we will get two answers. The first one is y approximately 8.838 and the second one is y approximately 2.829. Next, to identify which value is the maximum value, we have to use the second derivative test. After deriving the equation once again, we will get v double prime equals to 24y minus 140. Then, we have to substitute the variables with each value. The first value we will get 72.112 and the second one we will get negative 72.104. As stated in the picture, after substituting the value of variable, if the second derivative equation value is bigger than 0, thus the variable is minimum value. Meanwhile, if the second derivative equation is smaller than 0, hence the variable is maximum value. Therefore, y is equals to 2.829 cm since it satisfies the terms v double prime y is less than 0. Hence, the square size that should be cut are 2.829 cm by 2.829 cm.
In this assignment, we used related rate and calculus to tackle an optimization problem. We explored how to determine the best size for square cut from each corner of a material to create a box with the largest volume. By defining the side length of the square cut as, we derived a formula for the box volume and found the critical points by solving its derivative. This gave us two possible values for to confirm which value maximized the volume. We used the second derivative. The analysis showed that one value resulted in a maximum, leading us to conclude the optimal square cut size is approximately. This process highlights the practical power of calculus in solving real-world problems.